Coupled oscillator. New chapter, coupled oscillator. Okay. Introduction. For small oscillations, there is usually a coupling between two or more oscillators. When the motion of one oscillating system influences another, okay, the two are said to be coupled. The two or more oscillators link together in such a way that an exchange of energy transfer takes place between them are called coupled oscillator. Okay, the two or more oscillator, the two or more oscillators, and two or more oscillators linked together in such a way that an exchange of energy transfer takes place between them. Takes place between them are called coupled oscillator. Coupled oscillator. Okay. The two or more oscillators linked together. The two or more oscillators linked together in such a way that an exchange of energy transfer takes place between them are called coupled oscillators. In forced oscillator, it is assumed that the external driving force is practically not affected by the oscillations of the driving system. The flow of energy between the driving agency and the driving system is only in one direction from the driving agency to the driving system. However, in actual practice, there is always some feedback of energy, although small. In this chapter, let us study two coupled oscillators and their normal modes of vibration and extends the idea to n coupled oscillators. Okay, some definitions. Normal coordinates. Okay. Normal coordinates are those coordinates which help us to express the equation of motion of the harmonic oscillator of a body coupled system in the form of a set of linear differential equation with a constant coefficient, and in which each equation contains only one variable. Okay. Normal coordinates are those coordinates which help us to express the equation of motion of the harmonic oscillators. The equation of motion of the harmonic oscillator. Okay. Harmonic oscillators of a coupled system. coupled system. Coupled system of a coupled systems. Okay? Okay? Of a coupled system in the form of a set of in the form of a set of in the form of a set of linear differential equations. Linear differential equation. Linear differential equation with constant coefficient and in which is and in which each equation contains only one variable. Contains only one variable. Okay? Normal coordinates are those coordinates which help us to express the equation of motion of the harmonic oscillators of a coupled system in the form of a set of linear differential equation with constant coefficient and in which each equation contains only one variable. Normal mode of vibration. Normal mode of vibration. Okay? The manner in which a coupled system oscillates is called a mode. The mode of a coupled system may be harmonics or non-harmonics. The harmonic mode of coupled system are called normal modes. Okay? The manner in which a coupled system oscillates is called a mode. The mode of a coupled system may be the mode of a coupled system may be harmonic or non-harmonic. Okay? Non-harmonic. The harmonic mode of coupled system. The harmonic mode of coupled system. The harmonic mode of coupled system are called normal modes. Okay? The harmonic mode of coupled systems are called normal modes. Okay? Normal modes of vibration of initially normal coordinates Normal coordinates are those coordinates which help us to express the equation of motion of the harmonic oscillator of a coupled system in the form of a set of a linear differential equation with constant coefficient, and in which each equation contains only one variable, normal mode of vibration. The manner in which a coupled system oscillates is called a mode. The manner in which a coupled system oscillates is called mode. The mode of a coupled system may be harmonic or non-harmonic. Okay? The harmonic mode of coupled system are called normal modes. Normal modes have definite characteristics and are represented by linear differential equations. The normal modes have definite characteristics. The normal modes have definite characteristics and represented by linear differential equation with constant coefficient and only one dependent variable are normal coordinates. A normal mode has its own frequency known as normal frequency. In each normal mode, all the components of the system variable with the same normal frequency. The normal modes of vibration are entirely independent of each other since the energy associated with a normal mode is never exchanged with the energy associated with another normal mode. The total energy of the oscillator is equal to the sum of the energies of all the normal modes. If at any time only one mode is excited and vibrates, the other modes will always be at rest and unexcited, and these will acquire no energy from the vibrating mode. Okay? Degree of freedom. Next, degree of freedom. Okay? Degree of freedom. Next, degree of freedom. Degree of freedom. Okay? Degrees of freedom. Degrees of freedom. Okay? Degrees of freedom. Okay? A degree of freedom of a system is the independent way by which the system may acquire energy. A degree of freedom of a system, or degree of freedom of a system. A degree of freedom of a system is the independent way by which the system may acquire energy, by which the system may acquire energy. Okay? Or degree of freedom of a system is the independent way by which the system may acquire energy. Okay? And a degree of freedom is assigned its own particular normal coordinates. The number of degree of freedom and the number of normal coordinates of a system is the number of different ways in which the system can acquire energy. Each harmonic oscillator has 2 degrees of freedom, as it may have both kinetic as well as potential energy. Okay? Next point. The kinetic energy of a simple harmonic oscillator of mass m and having displacement coordinates x is given by the kinetic energy of a simple harmonic oscillator, simple harmonic oscillator of mass m and having displacement and having displacement having displacement coordinate x is given by 1 by 2 m differentiate of x square equal to a differentiate of x square, where a equal to 1 by 2m. Okay. The kinetic energy of a simple harmonic oscillator of mass m and having displacement coordinate x is given by 1 by 2 m differentiate of x square equal to ax square. Okay, where a equal to 1 by 2m. 1 by 2m. The potential energy is given by the potential energy is given by the potential energy is given by 1 by 2 s x square equal to bx square, where s is the stiffness constant, where s is the stiffness constant, where s is the stiffness constant. Okay, if the normal mode of a harmonic oscillator are represented by normal coordinate x and y, then the total energy corresponding to the two modes will be Ex equal to a differentiate of x square plus b differentiate of x square, and E lambda equal to c differentiate of y square plus d y square. Okay, where A, B, C, D equal to constant. Okay, constant. A differentiate of x square and C differentiate of y square gives the kinetic energy. Gives the kinetic energy, and bx square and dy square, bx square and dy square potential energy. Okay, next heading.